this video, we will be looking at exponential growth and decay. We have seen exponential functions before, and we know that they can either increasingly grow to the right or decrease to the right. So for growth, your dependent variable is increasing by a common factor. So it might look something like this. And the common ratio, or the base of the exponent, has to be greater than 1. And an application example of this would be something like a bacteria population or the value of a painting. For decay, your dependent variable would decrease by a common factor, so something like this. And the common ratio would be between 0 and 1. So an example of this would be an isotope mass or the value of a car. And for both of these scenarios, the domain and range is the same, where the domain is x is an element of all real numbers and the range is y is an element of all real numbers, but y is greater than 0. And that's because we have that horizontal asymptote at y equals 0. Now, these domain and ranges, they can change for application because you can't have negative time. Now, the initial value we know is the y-intercept, which in a exponential function we can label it as a. So we have a generic formula for word problems that are represented by exponential growth or decay, and that is f at x equals a times b to the power of t over per. So the a value represents the initial amount or quantity, so the initial population or mass or value. B represents your growth or decay factor. T represents the total time elapsed, and the per represents the length of the growth or decay cycle. So for example, if something is doubling every 5 hours, 5 would be the length of that growth cycle, and it would go in the denominator of that fraction. Now, something that's important is that your fraction, the t and the per, have to have the same units. And then finally, f at x is the final amount. For growth and decay, your formulas are like this, but the difference between your base is the fact that for growth, the base has to be greater than 1. And the way we do that is by adding our rate as a decimal to 1. So if my growth rate was 5%, 5% is 0.05, so I would do 1 plus 0.05, which is 1.05. For decay, my base would be 1 minus that rate of decay. So if my decay is by 20%, I would do 1 minus 0.2 to get 0.8 for my base. Now we also have two special scenarios that are called half-life and doubling life, or doubling time. For half-life, your rate is 1/2, and it usually applies to isotopes. So you might start with a certain mass, and let's say the half-life is 5 days. Every 5 days that mass gets cut in half. So if you start with 100, in 5 days you'll be at 50 grams. And then another 5 days you'll be at 25, and so on. And then same idea for doubling life, but you're doubling maybe the bacteria population. So the rate is going to be 2. Now let's look at 5 different equations here and make up a scenario to match them. So for the first one is P at t equals 5,000 times 1.02 to the power of t. Seeing P at t, I'm going to say maybe it's population, and let's say years. I'm making it up to match this. So the initial population is going to be 5,000, and it is growing at 2% per year, let's say. Because I know it's growth because my rate is greater than 1, and it looks like I'm adding 0.02, which means 2%. And because my fraction for my exponent is t over 1, that means that the growth rate is every 1 something. And because I've chosen years, there we are. So 5,000 initial population grows 2% per year. And there we are. The next one, m at d equals 280 times 1/2 to the power of d over 3. So I know it's a half-life, and it appears that the half-life occurs every 3 something. Maybe d is days and m is mass. So let's say we have 280 grams to start, and it has a half-life of 3 days. Okay, next one. B at H equals 18 times 2 to the power of H over 6. So maybe it's a bacterial population and something in hours. We initially have 18 bacteria and they double every 6 hours because of that denominator in the exponent. So 18 bacteria double every 6 hours. Next we have F at T equals 800 times 0.76 to the power of T over 2. So maybe we have a frog population here. So 800 frogs decrease by something every 2 years, let's say. Now to actually find your rate here, because you might not automatically see what you're decreasing by, you can do 1 minus 0.76, which is going to give you 0.24. So that means 24%. So 800 frogs decrease by 24% every 2 years. And finally, V at T equals 38,000 times 0.8 to the power of T. So maybe it's the value of a car. You buy a car for $38,000 and it decreases by 20% every year. And the way I got that 20% is by doing 1 minus 0.8, which is 0.2, and that means 20%. So a 38,000 car decreases in value by 20% every year. And there we are. Hopefully this allows you to see the effect of the base and that per idea. And the reason we have to divide our time by the length of the growth or decay cycle is because we want the exponent to represent the number of times that rate is applied. So if something is decreasing every 2 years and you want to see the population in 10 years, you can't just raise it to the power of 10 because it's not decreasing by that percentage 10 times. It's decreasing 5 times because in 10 years, the rate is applied 5 times. So that's where that division is coming from and why that fraction is important. So let's go ahead and look at our first example and try to create an equation and answer some questions. So Kathy grew a colony of bacteria as a science project. She started with the bacteria covering an area of 100 centimeters squared. 10 hours later, she found that the area had increased to 200 centimeters squared. So we can see that this is doubling from 100 to 200. So here they didn't actually give us the rate, but we have to notice that our rate is 2. Okay, so now, or that will be our base. So maybe I'll just put B for base. We're starting off with 100, and we're talking about a bacteria population area. So we have to start off with our let statements. Let A represent bacteria area. And then it was in hours, so maybe you can say let T represent number of hours or H, whatever you'd like. Let T represent number of hours. So my equation will start with A at T. I know that the initial bacteria area is 100. I know that it is doubling every 10 hours. So that means we're going to have T over 10. So we have our equation. Now we can answer our follow-up question. How many bacteria will there be after 15 hours, or the bacteria area? So that means we are doing A at 15. And notice it is in hours, so it's okay for us to just put 15 in for t. So 2 to the power of 15 over 10. And now you can go to your calculator and plug this in. And you get approximately, so I'm going to use squiggly equal signs, you get 282.8. You have to think for exponential functions and application problems, the rounding practice that you usually use will not apply. So this is 282.8. You haven't actually created the rest of that bacteria or that area to get to 283. So you do have to round down here to 282 centimeters square. So you haven't accomplished, like you have 0.8. So you're still missing 0.2 to actually get to 283. So for exponential functions, you can't round the way you normally do. You usually round down. So therefore, the bacterial area is 282 centimeters squared. Okay, let's go to the next one. Isotope AM241 has a half-life of 20 minutes. If the initial mass is 20,000 milligrams, write an expression to model this data. So we're dealing with mass, so let M represent mass, and we want to state that it's in milligrams. And let T represent the time, and because the half-life is given in minutes, time will be in minutes as well. And it's important to state that because if something isn't given in minutes, you have to convert it into minutes. So M at T equals, the initial mass is 20,000. The rate, because it is half-life, will be a half for 0.5. And because the half-life is 20 minutes, we will have T over 20. All right, for the next two, what is the mass after 1 hour? And what is the mass after 3 hours? In both of these, the time is given in hours, but our equation is in terms of minutes. So 1 hour is the same as 60 minutes. So we're going to do T equals 60. So in my equation, I'm going to evaluate M at 60. So that's 2,000 times 1/2 to the power of 60 over 20. And 60 over 20 is 3. So that means that that rate of a half is applied 3 times in that hour span. And when you plug that into your calculator, you get exactly 2,500 milligrams. So then you would write your therefore statement of, therefore, the mass is 2,500 milligrams after an hour. So I want you to pause the video and try C on your own and then come back to check your work. All right, so 3 hours is the same as 180 minutes. So we have to replace T with 180, and when you do that, you get 39.0625 milligrams. And then make sure you have your therefore statement. Okay, let's sketch this relation. And because it is a word problem, we do have to think about some things that will not continue. So for example, our initial population was 20,000. So I'm going to label that point. And I'm also going to put M here for mass and T here for our number of minutes. So number minutes and then mass in milligrams. So make sure you do label your scale so that people know what is going on here. So if we start at 20,000, we're not going to be super accurate, but I know in 20 minutes it will be cut in half. So I will just apply that half-life once or twice just to get a more accurate sketch. So in 20 minutes, we would be halfway at 10,000. And then another 20 minutes, so at 40, we would be halfway of that, so 5,000. And then once the reader gets an idea of what's going on, you can just extend and continue. Now, now that we have our sketch, we can do a little domain and range. And the domain and range will not be the same as regular exponential functions. First of all, we don't have x and y, so make sure you're using the appropriate variables. So for domain, it's going to be time. So time is an element of all real numbers, except time has to be greater than or equal to 0. And then it can technically go on forever. Then for our range, it is not y, it is our mass. So the mass is an element of all real numbers, except it's not going to go on forever upwards. We do have a restriction of that 20,000 because that's what we're starting at, and it won't ever touch 0 because with exponential functions there is an asymptote there, and if you cut a number in half, it will never actually reach 0. So even if you're cutting 1 in half, you get to 0.5, then 0.25, then 0.125, and even cutting a really, really tiny number, you're still never actually mathematically going to reach 0. So we're just going to say that the mass is between 0 but not equal to 0, and then less than or equal to 20,000. And there we are. Now here's one more type of question where we apply our knowledge of solving exponential equations. How long does it take for the isotope to decay to 90% of its original mass? So the first thing we should do is find 90% of the original mass. So we do that by multiplying our original mass by 0.9 because that's 90% as a decimal. And when we do that, we get 18,000. So now we're given our mass of 18,000, and we can set our equation equal to 18,000. And it will look something like this. And now we know we can't go to that common base idea until we get rid of the 20,000. So we're going to divide both sides by 20,000. And when you do that, you get 0.9. And I'm just going to turn that 1/2 to 0.5. Now sometimes you might get a decimal or a nice fraction that looks familiar, but 0.9, which is 9 over 10, and then the 1/2, you're not going to be able to get a common base with that. So there are two ways that you can solve this. At this point in time, we don't really know how to solve and get the common base, so it would become a guess and check, where you try to get a common base of 0.5, and you do 0.5 to the power of anything to try to get 0.9. So it becomes this guess and check type of thing. So for example, maybe I'll try 0.5 to the power of 2. That gives me 0.25. 0.5 to the power of 5, 0.03125. So going higher isn't helping me with anything. So I actually need to go a little lower. So 0.5 to the power of 0.5, that's 0.7. 0.5 to the power of 0.4, that's still the same thing. To the power of 0.2, that's 0.87. I'm getting really close now. So maybe I'll try to the power of 0.15, and I get that 0.9 that I want. So that's using a bit of guess and check, where I try to take the 0.9 and turn it into the same base as the term with the exponent that is a variable. So I can rewrite 0.9 as 0.5 to the power of 0.15, and that is just guess and check. Now that is very tedious, okay, and I will show you another way to do this. But right now we have a common base, so we know once we have a common base, we can just set our exponents equal to each other. And here, I'm just going to put my 0.15 over 1 and do a quick cross multiplying, where I do t times 1 is t, and then 20 times 0.15 is 3. So that means it takes 3 minutes for the bacteria to decay to 90% of its original mass. Now, I'm going to show you a shortcut to get this 0.15 quicker. And that shortcut is using the log button. So what you can do in your calculator is do log of the number you want to change the base of, so log 0.9, and divide it by log of the rate. And if you do log of 0.9 divided by log of 0.5, you get 0.152, and this is a lot more accurate than what I put down. If I had used 0.152, my answer could have been a bit more accurate. So this is a great shortcut instead of doing that guess and check. But sometimes you will get lucky and you will know the common base right away. Now, therefore, it takes 3 minutes for the bacteria to decay to 90%. All right, let's try another example. All right, Mr. Johnson's hound weighs 43 pounds. Mr. Johnson found a diet that claims to decrease the dog's weight exponentially by 1% each day. Create an equation that models this scenario. So let's start off with our let statement. So we are talking about weight and the number of days. So let W represent weight, and it is in pounds. And we can use D for days. Let D represent number of days. It doesn't always have to be T for time, whatever you'd like. So we have W at D. The initial weight is 43, and it is decreasing by 1%. So for our rate, for the base, we're going to do 1 subtract 0.01, because that's what 1% is as a decimal. And if we simplify it, we get 0.99. And it occurs every day, so it's just going to be to the power of D. And you can write that as D over 1 if you'd like to, but this is enough. So now, how much will his hound lose in a week? So for a week, we're talking about 7 days. So we can just put 7 in for D. And when we plug this into our calculator, you get 40.0788. So we can just round that to, let's say, 40. So the hound will weigh 40 pounds in a week. So that means it will have lost 3 pounds. So therefore, the hound will lose 3 pounds. Okay, let's do a little sketch. We're talking about the weight in pounds, and we're talking about D, the number of days. And here we know that the starting weight is 43, and then it would decrease. Now, when you do your decrease, don't make it look something like this, because you really don't want a dog to weigh almost 0 pounds. So I'm just going to, before I draw in my sketch, I'm going to continue and read question D to kind of know when I should stop. If the vet says Mr. Johnson's hound should weigh 31 pounds, how many days should Mr. Johnson keep his hound on the diet? So when I draw my sketch, maybe I'll just kind of stop it around a 31 mark. Okay, so if we want the hound to weigh 31, then we will set our equation equal to 31. And now, I want you to pause the video and try to solve this. Use that little log trick to get the common base, and then come back to check your work. All right, so first thing, we're going to divide both sides by 43. And I'm just going to keep that 31 over 43 because I don't want to cut down on my decimals. And now, to get that common base, you want to do log of that 31 over 43 divided by log of 0.99. And whatever you get here, that's what your other exponent will get set equal to. So if you do that, you get 32.557. So that means 0.99 to the power of 32.557 will give you that 31 over 43. Now you have to think here how you want to round. Typically we would round this up to 33 days, but we should test both to see what will actually give us that weight of 31. So if we try 43 times 0.99 to the power of, let's say, 32, the weight is 31.17. So the dog hasn't actually reached 31. It is still a little bit over. If I go to 33, then the dog will be 30.86. So it has dropped down to that 31 weight. So we're going to round this to 33 days. So therefore, the hound should stay on the diet for 33 days. And now using this information, let's do our domain and range. So for the domain, we know we are talking about the number of days. So D is an element of all real numbers. We know we can't have negative days, but also we know that the diet stops at day 33. So D is greater than or equal to 0, but less than or equal to 33. And then our range is about the weight. So the weight is an element of all real numbers. And we know that the weight started at 43 and it's going to stop at that 31. So 31 is less than or equal to the weight, and the weight is less than or equal to the 43. And there we are. So with the domain and range, you have to think about your scenario and restrictions on application variables, not just a regular X and Y. All right, let's try our next one. Uranium is a radioactive element with a half-life of 1 year. The sample begins decaying in 2017. Write an equation to represent the amount of uranium remaining, A at T, as a function of the number of years, T, if you have an initial sample of 45 grams. So we were given our let statements already, so we don't have to worry about that. We know the initial sample is 45 grams. We know it's a half-life of 1 year. So I want you to pause the video and try to write that equation out on your own and then come back to check your work. So your equation should be 45 times a half to the power of T, and you can write that as T over 1, but you don't have to. Now, for B, how much of the substance was lost or decayed by the year 2025? Round to 3 decimals. So we need to figure out the mass in 2025. But first, we have to figure out what we should plug in for T, because you are not plugging 2025 in, because that would be 2025 years after 2017. So to find our time, we'll do 2025 minus 2017, and that is 8 years later. So we're going to plug in 8 for time. So I want you to pause the video, plug that into your equation, and then tell me how many grams were lost. All right, so when you plug in 8 for time, you're going to get 0.176 grams. That's the number of grams that will remain in your sample. That's not how much was lost. So if I want to know the loss, then I'm going to do 45 subtract that 0.176 to get 44.824 grams that were actually lost. So in this scenario, you just have to read it a little more carefully to get the final answer. It's not just plugging into your equation. And now let's try our last one. Due to a wet summer, the mosquito population in Newmarket has been rising. The current mosquito population measures 530,000 and it is growing at a rate of 1.2% per day. Write an equation to model the mosquito population P at D after D days. So we know our initial population is 530,000. And we are increasing by 1.2% per day. 1.2 is the same as 0.012, so we're adding that on to 1, which means 1.012 to the power of D. And it's per day, so we don't have to worry about dividing D by anything. So what will the mosquito population be in 30 days? So go ahead, use your equation to answer this question, and then come back to check your work. All right, so when you put 30 in for D, you should get 758,038, and it was 0.46, so we rounded down. Now, create an equation that models this scenario based on the mosquito population doubling. So that means they want the equation to be P at D equals 530,000 times 2 to the power of T over something. We need to figure out when the mosquito population doubles so that we can fill in that blank. So they just gave us a new rate and we have to make that work. So first thing we should do is double 530,000, and when we double it, we get 1,060,000 mosquitoes. Now we can set our equation equal to that, and now we're just going to solve for our number of days. So we're pretty much rewording this right now to after how many days will the population double. So I want you to pause the video here, solve for D, and then we'll put that final equation together when you come back to the video. So when you divide both sides by 530,000, you're going to get 2. And now we're going to use that little log trick and do log 2 divided by the common base we want. And when you do that, you end up with 58.108. Now, you have to decide if you should round that up or down. And the way we do that is by testing it into our equation. So if I do 530,000 times 1.012 to the power of 58, which is how I would normally round, I haven't actually reached double the population. So 58 is no good. But if I round up, which I wouldn't normally do, then I have surpassed that 1,060,000. So we would consider 59 the doubling time. And now that we have that, we can go to our equation and do T over 59. And that will be the new equation that represents the mosquito population doubling. So anytime you want to rewrite your equation in terms of a different rate, you just have to solve for how long it takes for that specific rate to apply. And that's it. So just remember, for an exponential equation, the first number is your initial population. The base is your rate of either growth or decay, or half or double. And then your exponent will be how often that rate is applied. So it might be T over a number or whatever it might be. And for these types of questions, I can actually give you the time element, or I can give you the final amount. So you have to solve an exponential equation. Maybe you'll have to do a sketch, do domain and range, and that kind of thing.